This is calculus 2. We keep working on the series. This is part 2. We're gonna discuss telescoping sum and geometric series. Previous slides, previous video, we talk about partial sum, definition of infinity series. I give the specific series. We're gonna find sum of infinity series. Let's try to find a telescoping sum. This one is gonna be, looks like this form. Infinity series is left side is this form. That's the 1 over I plus 1. What do you have to do? We have the partial fraction decomposition. So we have 1 over I minus 1 over I plus 1. Now, this one is a sequence. We have to find the partial sum. Partial sum is Sn summation I equal 1 to n 1 over I minus 1 over I plus 1. Let's find the partial sum first. Plug in the each I value, okay? I equal 1, 1 minus 1 over 2 plus I equal 2, 1 over 2 minus 1 over 3. Keep going until I equal n. That's the last term, right? That's 1 over n minus 1 over n plus 1. Now, we want to find before the last term. Last term is I equal n. Before the last term, I should be n minus 1. So we want to find this term, 1 over n minus 1 minus 1 over n. When you see this each term, what do you see here, guys? Look at C. 1 over 2, cancel out 1 over 2. Negative 1 over 2, positive 1 over 2. 1 over negative 1 over 3, positive 1 over 3. So this one is a 1 over n minus 1, cancel previous term. Negative 1 over n, cancel right here. So what are you left here? Here is 1. Here is negative 1 over n plus 1. That's the partial sum of this sequence. Now, after you find the partial sum, we want to find the limit of this partial sum. Let's just take a limit. Limit n approach to infinity Sn, limit n approach to infinity 1 minus 1 over n plus 1. 1 over n plus 1, this going to 0 and approach to infinity. So this partial sum gonna be 1. So we find the sum about this infinity series. So conclusion is summation I equal 1 to infinity 1i, I plus 1 is gonna be 1, and this series is gonna be convergent. Here is when you see this kind of series, guys, first thing is you expect you're gonna cancel out some terms between the first one and last term. That's you have to figure it out first. So specifically this kind of series we call telescoping series, okay? Telescoping sum, telescoping series. Okay, I'm gonna give another example here. Let's do another example of telescoping. So here is the original series, looks like ln I plus 1 right there. What you have to take a first step is you're gonna expand ln. So expand ln is ln I ln I over I plus 1 equal ln I minus ln I plus 1. That's you're going to expand the ln. You're going to clearly see the reason why I expand the ln sequence right here, because we want to cancel out something. So we have to find the partial sum Sm first. Sm meaning is summation I equal 1 to n, each sequence looks like ln I minus ln I plus 1. So we're going to find each term from sigma. So I equal 1, ln 1 minus ln 2. I equal 2, ln 2 minus ln 3. Keep going to I equal n, ln n minus ln n plus 1. Before the last term, I equal n minus 1 right here, ln n minus 1. Need a space right here, guys. ln n minus 1 minus ln n. See that? Here is, this one is I equal n minus 1. So now, after this you did, look at this one. What is cancel out? ln 2, here is negative positive, ln 3, ln n minus 1, previous term, ln n minus 1, ln n, ln n. That's cancel out. What you left here, ln 1 minus ln n plus 1. So only Sn partial sum gonna be ln 1 minus ln n plus 1. ln 1 is gonna be, this one is 0. So we're gonna take a limit of Sn, limit negative ln n plus 1. Here is negative limit and approach to infinity. That's gonna be ln n plus 1. ln is ln function go to where and approach to infinity. This going to infinity, that's going to be negative infinity. Which meaning is this series here, this partial sum is divergent. So we're going to say this is going to be divergent. Okay, that's we're going to find or evaluate telescoping sum. If your telescoping sum is convergent, we can find the sum of infinity series. Now we're gonna do geometric series. So sum of geometric sequence. So let's have some of geometric series, guys. As start point is, what is geometric series? Looks like this one. Summation AR n minus 1. Here is right here. A plus AR plus AR square. That's we're gonna have some of geometric sequence. When this geometric sequence is convergent, here is condition R is ratio going to be negative 1 and 1, and this sum is going to be A over, that's the first term, 1 minus ratio. That's going to be geometric series, sum of geometric series. Let's going to be prove this one, guys, okay? So I'm not going to go detail prove a partial sum of geometric series. So Sn gonna be partial sum geometric series gonna be A 1 minus R and 1 minus R. That's partial sum of geometric series. So first condition is R is between negative 1 and 1, which meaning is limit and approach to infinity, Rn going to 0. We know this one is geometric sequence. Now, let's take the partial limit of partial sum Sn, limit and approach to infinity, A, 1 minus Rn, 1 minus R. Then what happened? R is ratio going to be between negative 1 and 1, Rn going to 0. So this part going to 0. Now, what do you have? This limit of partial sum is A over 1 minus R. That's you're going to prove first part. Now, geometric series convergent when R is negative 1 and 1, between the negative 1 and 1, guys, very, very important. Then we're going to have sum of geometric series A, first term, 1 minus R ratio. That's we're going to find geometric series. So other cases, what happened? R is, we only check R is between the negative 1 and 1. Now we have checked R is 1, R is 1, R is greater than 1, less than negative 1, R is negative 1. Let's check R is 1 here, guys. What is R is 1? What happened? This geometric series looks like A plus A plus A plus A plus. The case Sn partial sum gonna be A plus A plus A plus how many A? This one is N. So this n Na, limit n approach to infinity Sn, limit n approach to infinity Na. A is constant A, limit n approach to infinity N, that's going to infinity. So this one is divergent. R is 1, the case. That's the divergent. Let's keep check if R is greater than 1, less than 1, or R is negative 1. Now, what you did the previous slides, we proved R is between the negative 1, positive 1, that's converse, that's the sum of geometric series. And we prove R equal 1, then also divergent. Now, what you have to prove it? We have proved R is going to be greater than 1. R is greater than or R is negative 1. Another case is R is negative 1. Let's check both, okay? R is negative 1. What happened? So here is going to be geometric series. Going to be looks like A or n minus 1 going to be A minus A plus A minus A. That's what we're going to see right there, right? So how can find this limit? So it depends how many terms you add. Look at this. S1 is A. S2 gonna be 0 because A minus A equals 0. S3, A minus A plus A, that's gonna be A. S4 gonna be A minus A plus A minus A, that's gonna be 0. That's alternating. This partial sum is alternating. A0, so limit Sn is diverse. Okay, so that's why R equal negative 1 also diverse. R is greater than or less than negative 1. Sm, partial sum, A, 1 minus Rn, 1 minus R. What happened, Rn? That's divergent. So we cannot say limit Sn is convergent. So this is diverse. Here is series sum of geometric sequence. So we have to first recognize if this series is going to be geometric series. How do you know? Each term AR scale, each time they times R. Okay? Then R should be between the negative 1 and 1 converse. R is greater than 1, less than 1. R is 1, R is negative 1 diverse. R is, you have checked, R is between negative 1, positive 1. You can find the sum, first term over 1 minus ratio. That's how to find the sum of geometric series. Now let's thinking about convergence divergence of the series. So let's start with A. Okay, this one is a summation n equal 1 to infinity 3 over 2n. You have no idea if this series is going to be geometric series or not. You're going to expand this series here. So n equal 1, 3 over 2. N equal 2, 3 over 2 square. N equal 3, 3 over 2 cube. So what kind of sequence here, guys? Look at this. Each time you have 1 over 2. You have times it, you times A1. R is going to be 1.5. So R is between the -1, +1. So this one is convergent. Then you can find the sum. Sum gonna be first term, 3 over 2, 1 minus 1.5. So this one is 3 over 2, 1.5. This one, 3 over 2 times 2 over 1. That sum gonna be 3. So we find the sum of a geometric series right here. This is a 3. Okay, let's go next one. Next one is gonna be B. Same thing. I think you notice this is a geometric series because something power n. So just in case you cannot recognize this is geometric series, you're gonna expand this with 3 over 2, 3 over 2 square, 3 over 2 cube, like that. What is R gonna be? Each time you times 3 over 2, 3 over 2. R is 3 over 2. This is definitely greater than 1. So this one is diverge. What is the important thing is you figured it out. If you see the series, there are so many different theories. This one is you have to recognize geometry. More example about geometric series. So let's check this is geometric series or not. First, can you see that this one, each term you times 1 over 10. R is 1 over 10. Then check the condition for convergence of geometric series. So R is, so how can find it? R10, R10 square, R10 cube. This geometric series is gonna be A1. First term is, this one is A1. 8 over 10, 1 minus R is 1 over 10. 1 over 10. So this one is A over 10, 9 over 10. This one is 8 over 10, 10 over 9. So this one is 8 over 9. So this sum gonna be 8 over 9 of geometric series. So let's check it out. This is a 5. How can find 10 over 3? Negative 10 over 3. Go to next one. You cannot see the what is the ratio right away. So check it next terms. First, this is first term. This is the second term. Much clearer, right? Negative parts, alternating series, alternating geometric sequence. So this case, what is R gonna be? R gonna be negative 2 over 3. Can you see the 10 over 3 times negative 2 over 3 plus 20 over 9. Same thing is here. 20 over 9 times negative 2 over 3, 40, negative 40 over 27. So you find R is negative 2 over 3. So first term is a 5. But R is here between 1 and negative 1. So this one is converse. What is this sum? Gonna be A1. 5, 1 minus negative 2 over 3. This one is a 5. 1 plus 2 over 3. This one is a 5. 5 over 3. This is 5 times 3 over 5. That's gonna be 3. So you find the sum of geometric series here. Let's do more geometric series. It doesn't look like geometric series. Let's check it out. So you're confused about geometric series. First you expand it, then you're gonna see this one is geometric series or not. So let's expand it. First one is 2, 1, 3, 1 minus 1. Second is 2 square, 3, 1 minus 2. Third one is 2 cube, 3, 1 minus 3. Keep going, right? So 2 times 3, 0 is 1. 2 square, 3 negative 1. 3, 2 cube, 3 negative 2. This one is 2. 2 square, 3 negative 1 is 3. 2 cube, 3 square, like that. Can you check it out? This is geometric series or not? Let's check it out. This one, what happened? You have times 2 over 3. What happened here? 2 over 3, right? The ratio is 2 over 3. Good news is this is between negative 1 and 1. So this one is convergent. What is the sum? First term is 2. 2, 1 minus, ratio is 2 over 3. So 2 over 1 over 3, that's going to be 6. This geometric series is convergent. This is another example is, this one is, let's expand it, or you can see this one is geometric sequence, right? This one. So an is 5 over 2n, right? So this one is gonna be expanded 5 over 2, 5 over 2 square, 5 over 2 cube. So this one ratio gonna be each time r is 5 over 2, 5 over 2, 5 over 2. This one is greater than 1. So our conclusion is this one is diverse. So when you see the geometric series, at first you have identified this series is going to be geometric series. Then you check the ratio. Ratio is between negative 1 and 1. That series is going to be converged and you can find the sum. What you studied so far is definition of both infinity series. We define the partial sum, limit of partial sum of infinity series. Limit of partial sum is converse, infinite series converse. After we study definition of infinity series, we study two different kind of infinite series. First one is telescoping sum, second is geometric series. Both case, if series convergent, then you can find the sum. Not all the time we can find the sum of infinite series if the series convergent. So we're gonna start test for divergence. Before you start, let's prove this theorem first. So this one is summation n equal 1 to infinity series conversion, meaning is we're gonna say partial sum gonna be convergent. So which meaning is limit of partial sum has limit s. Let's talking about limit of Sn minus 1. Looks like a symbol are different, but that's part of sequence. So here is partial sum is S1, S2, S3, S4, Sn minus 1, Sn. We using Sn symbol. This approach, this whole sequence partial sum going to S. That's the meaning of conversion. So limit of n minus 1 and approaches infinity, they also going to S. Based on this information, we're going to find an. Guys, what is an? From the partial sum, Sn minus Sn minus 1. See that? This meaning is A1 plus A2 plus all the way an. Before the an minus 1 minus A1 plus A2 all the way an minus 1. So this one is subtract. You're going to cancel out everything except A1. That's you're going to have an. Now, let's take a limit of this sequence. Limit n approach to infinity, limit n approach to infinity, Sn minus Fn minus 1. So this one is limit Sn minus limit Sn minus 1. This is S minus S. This is 0. So here is very important thing. This one is converse, then sequence is gonna be converse, series gonna be converse, sequence is converse. Okay, that you have to remember. What did you talk about previous slides? We talk about if sequence series gonna be converse, limit of an gonna be 0. But this Anstem test for divergence is very careful. Here is what condition we have. Limit of sequence is not 0. Very important, guys, here. It's not 0, or limit of sequence does not exist. We say series is going to be divergent. Okay? For example, it's going to be here, guys. Let's say, I'm going to give the example later, but here's very careful things you have to see from now on, guys, right here. If limit of sequence is 0, it does not guarantee that series gonna be converged. Let's give the example of this statement. So I'm gonna give an is 1 of n. So then we're gonna talking about series. So an is 1 of n. So limit n approach to infinity, 1 of n going to 0, right? But this series, we're going to prove later, this is diverse. Okay, so this general term of sequence going to 0 doesn't guarantee infinite series is going to be converged. So make sure this one is Anstem test for divergent. Divergent condition is limit of sequence is not 0 or the limit does not exist. This one is divergent. If an going to 0 doesn't guarantee this is converged, this is going to diverge. We're going to use different tests. Later, we will learn. Let's practice Anstem test for divergence. Guys, here is emphasize this one is divergent, not the convergent. So this Anstem test for divergent. So we're gonna do first one is find an. N is n squared 5n plus 1. So find the limit n approaches to infinity, n squared 5n plus 1. This is gonna be L'Hopital rule. You can use this going to infinity, this going to infinity. So limit n approach to infinity, 2n over 5. Where do you go? This limit go to infinity. So this an go to infinity. This series gonna be diverse. Okay, that's you're gonna use this test. Second one is what is an there? 3n plus 5, 2n minus 1. Find the limit of this. 3n plus 5, but 2n minus 1. This one is also, you can use L'Hopital rule. Limit n approach to infinity, 3 over 2. This limit is going to be 3 over 2. This one is not 0. So what are you going to say? Second is also diverse. Only this test talking about divergence. Okay, let's go to C. An gonna be negative 1n. So limit n approach to infinity, negative 1 and n. This alternating sequence, so this might be a go to 1, next one is -1, 1, -1, 1, -1. This one is diverse. So which meaning is, or we're gonna say this limit does not exist, then we're gonna say this is diverse. So the nth term test for divergence, general term of a sequence is not going to 0 or limit does not exist, we confidently say infinite series is gonna be divergent.